Hello, welcome to this quick review looking at equilibria in the first year. So it's obviously meant to be an introductory video. It's useful to have made sure you've done some independent study notes on the topic before beginning, and if you've got a flashcard on LeChatelier's principle and also dynamic equilibrium, that would also be really useful. And we'll also look at a short exam question at the end to see how you can apply all of this. So Henri Louis LeChatelier proposed that when a system in equilibrium is subjected to an external change of some kind, it will readjust itself, the system will readjust itself to minimise any effects of that change. So when we talk about dynamic equilibrium, what we mean is a reaction where the rate of the forward reaction is equal to the rate of the reverse reaction. So the reaction has to be reversible for this to work. And the concentrations of the reactants and products remain constant, but they don't necessarily stay the same as each other. So sometimes what people do is they think that what this means is that the concentration of reactants equals the concentration of products. This is not true. It might happen to be coincidentally true, but it doesn't mean it happens all the time. What actually means is the concentration of the reactants remains the same throughout the reaction, and at the same time the concentration of the products remain the same throughout the reaction. So to achieve this, the rate of forward reaction has to equal the rate of the reverse reaction. So what we mean is that the reaction will proceed in whatever direction offsets the effect of any change. So if we take this idea in terms of temperature, this means that heating the reaction mixture will make what we call the position of equilibrium shift in favour of the endothermic direction so as to use up the excess energy. And if you cool a reversible reaction, it makes the position of equilibrium shift in favour of the exothermic direction so as to make more energy. So when we talk about the effect of pressure on a dynamic equilibrium, this is usually applied to homogeneous gaseous mixtures where all the reactants and products are gases. So if we think about pressure in terms of how many moles of gas are present, increasing the pressure shifts the position of equilibrium in favour of the side with fewer moles, as this reduces the pressure back down again. But if you decrease the pressure, this will shift the position of equilibrium in favour of the side with more moles, as this will move the pressure back up again. So with gases, for this to actually work, the system has to be closed, so the container has to be sealed, so no reactions can get in or out of it. So if we were to plot concentration of reactant and product with time, you could see when equilibrium is actually achieved. So for this particular graph, it would be N2O4 decomposing or breaking up into 2NO2. And the point at which the concentrations remain constant is when equilibrium is achieved. So here's another way of showing these ideas graphically as well. So the first graph shows obviously how the rates become constant. So the forward rate equals the reverse rate and they remain constant at a certain point. And you can think about the amount or the concentration of reactants and products, and when they start to become constant, as in here for the reactants, and here for the products, and at this point equilibrium has been reached. So this idea is used quite a lot in the chemical industry, because many products are actually made using reversible reactions. So let's have a look at a couple here. So we want to introduce the idea of compromise conditions that allow us to balance rate of reaction against yield at equilibrium. So what we're really after is a balance between how quickly equilibrium is reached and how much desired product do we get once that happens. And the problem is that these two things often require different conditions to each other. So increasing one might decrease the other, hence why we have to have the idea of compromise. So if we look at the Haber process, for example, we want the reaction to make as much ammonia as possible, as quickly as possible. So the forward reaction going from left to right is the one that we want. So to get it to make the ammonia as quickly as possible, we want to heat it up, because that will increase the rate of successful collisions between the reacting particles. Okay, so let's look at what happens when you actually do that. You may actually get a faster rate of reaction, but the equilibrium shifts in the opposite direction that you want it to go. In other words, it goes in the endothermic direction. So like we mentioned before, what happens is the position of equilibrium shifts in the endothermic direction to readjust for the added temperature. It has obeyed LeChatelier's principle. So essentially the choice we've got to make is between high yield but taking a long time to get to equilibrium because it's a slow reaction, or a low yield but a fast reaction. So the problem is that neither of these options make enough ammonia at a quick enough rate. What you've got to remember is industrial chemistry is about making money. It's about producing enough of your product quickly enough to turn a profit. So what we do is use a compromise set of conditions. It's not perfect, but it's the best we've got with the opposing constraints of the reaction. So we could use high pressure, for example, but then that would need expensive reinforced industrial plant. It could be dangerous if it breaks, or it could be expensive to actually build. So I've summarized for you in a little box what the conditions, the compromise conditions that are actually used in industry to produce ammonia. It's worth pausing and maybe putting them on a flashcard before we go any further. So the next thing that we're going to look at is something called Kc, how we mathematically work out the position of equilibrium. So all Kc is a way of mathematically expressing how far in one direction or another the position of equilibrium has shifted. So all Kc is really is the ratio of the concentration of the reactants to the concentration of the products. And it's also a unique and fixed value for each individual reaction. So what do the diagrams mean? So firstly, in the upper diagrams of the two, if Kc is less than 1, the concentration of the reactants must be greater than the concentration of the products. So if you look at the Kc expression in the box, the denominator, the lower term, is larger than the numerator, the upper term. So the overall effect of this mathematically is to make Kc smaller. So the smaller the value of Kc, the more the position of equilibrium has shifted to the left. However, if Kc is greater than 1, then the concentration of products is greater than the concentration of reactants, meaning that the numerator in the Kc expression is larger, the concentration term for the products is larger, so because a larger number is on the top part of the expression, Kc itself will be larger. So in this Kc expression for the Haber process, you can see that the concentration term is basically the product or reactant inside a set of square brackets. Each concentration term is raised to the power of the number of moles that that particular substance is found in the balanced equation. So, this is an example of a homogeneous equilibrium mixture because all the reactants and products are in the same physical state. So if we take a square bracket to represent moles per decimeter to the -3, that's one concentration term. And if we put all the concentrations terms side by side, you'll see there's quite a few. There's 4 on the bottom, and there's 2 on the top. Now the 2 on the top and 2 of the 4 on the bottom can cancel each other out like that. So now that obviously means we can write this out in simplified form, like 1 over mole squared decimeters to the minus 6, or alternatively, moles to the minus 2 decimeters to the power of 6. So it should be fairly obvious that the exact units of Kc depend on the number of concentration terms that are present in the Kc expression. So now it's time to have a look at an examination question. So this question's from an earlier specification, so it doesn't have any Kc work on it, but it's well worth having a look at anyway, because some of it is a little bit applied and thought-provoking. So you have a hydrogen and iodine reaction forming hydrogen iodide. All of the products and reactants are in gaseous form. And just having a look at the equation, you can see quite clearly that it's endothermic in the forward direction, because it says delta H equals plus 53 kilojoules per mole, and it's also equimolar both sides. 2 moles of hydrogen iodide on the product side, and 1 mole each of hydrogen and iodine on the reactant side. So 2 moles of gas each side. So first of all, it asks you to explain the observation that when the temperature is increased, the purple colour becomes paler. So you can see from the equation that the purple colour is obviously the iodine. So that must mean that the iodine is being used up, which in itself must be meaning that the equilibrium position is shifting to the right. But it's a 2-mark answer they require, so you've got to say why that might be happening. So it's due to the forward reaction being endothermic. So when the pressure is increased, the purple colour becomes deeper. This is because the iodine molecules move closer together due to the increased pressure. But like we said earlier, there's same amounts of gas either side, so pressure shouldn't really affect the equilibrium. So you need to state that, and the reason why is the equal number of moles of gas on each side. So you'll see that I'm ticking as I'm going, so you can see how the marks are being allocated. So that was a 3-mark answer there, that second section. So 1 for stating about the iodine, and 1 for stating about equilibrium position remaining unchanged, and 1 for mentioning the equal moles of gas on each side. The next part of the question is about reaction rate. In other words, how long does it take to reach equilibrium? So if you increase the temperature, there's more collisions between reactant molecules, and the collisions have energy equal to or above the activation energy. So there's 2 separate statements in there, so therefore 2 separate marks. If you increase the pressure, what's happening is that the molecules in the reactants are closer together, so therefore the rate at which they undergo successful collisions, or the frequency of successful collisions, will go up because of this. So that also gains a mark. Moving over to part C, there's a graph there, the concentration time graph, and you've got hydrogen gas, hydrogen iodide gas, and iodine vapour. Now, unfortunately, the lines on the graph are a little bit unclear, so I've drawn over them to try and emphasise where they are, so you can see them on the clip. And the first part asks, what change was made to the mixture at time t? So to make the graph reading a little easier, I'm just going to pop a line there so you can see where they're talking about. So if you look at the hydrogen concentration graph at the top, obviously that means that the hydrogen went up. So more hydrogen must have been added at that point. If you move down to the HI and the I2 lines, then it asks you to talk about them, because that's the equilibrium mixture. So clearly you need to say something about hydrogen iodide, and you need to say something about iodine vapour. So therefore the hydrogen iodide goes up, and at the same time the iodine vapour goes down in concentration, until a new equilibrium is established where the lines level out. Okay, so that takes us to the end of this short review of equilibria for year 1. Hopefully it's been reasonably useful in introducing you to some of the ideas. But in the meantime, thanks for listening, and until next time, see you soon.